All right. Please turn in homework number 9. And, all right. And then we're going to finish up section 11.10 today, start to do a little bit of review stuff. Monday we'll do some more review stuff. And then on Wednesday is the test on chapter 11 from section 1 through 10. Also on Wednesday, then the next homework and the take-home quiz are due. Okay. So, what we're talking about here, or in this section, are ways that we can represent functions as a power series in a much more general way than we did in the previous section. And it's called expanding them as Taylor series or as Maclaurin series. So let me write down again the formulas for the Taylor and Maclaurin series. For the Taylor series, oh yeah, we got to do, thank you. Let's see if we can adjust this here a little bit. There we go. Yeah, thank you. For the Taylor series centered at, say, x equals to a, then the formula is f of x equals the summation n equals 0 to infinity. And then it's the nth derivative of f evaluated at that number a divided by n factorial times x minus a raised to the n power. And then this is for x minus a, the absolute value less than some radius of convergence. Now I do want to tell you though that the notation includes, for n equals 0, the notation, what would be f0 of a is just another way of representing just the function f of a. It's just a notational thing. So that very first term is just the function itself. All right, so this expands out as f of a as the first term. Then we get into the derivatives f prime of a divided by 1 factorial times x minus a to the first power plus f double prime at a divided by 2 factorial times x minus a raised to the second power, etc. Okay, that's how it expands out. All right, then there's a particular example or type of Taylor series called the Maclaurin series, and that's just when x is equal to 0. So when we're centering it around, centered at 0, we have the Maclaurin series. Okay, and that looks pretty much just like this, except we put zeros here, so that's the summation, n equals 0 to infinity. Again, the nth derivative, except this time it's evaluated at 0 over n factorial, and then it's just x to the n power, because all it is subtracting 0 from x. And then this is for absolute value of x less than some radius of convergence. And this expands out. The very first term is not a derivative, it's the function evaluated at 0. And then we have f prime at 0 over 1 factorial, which is just 1, times x plus f double prime at 0 over 2 factorial times x squared, on and on from there. Okay. These don't always converge. Well, we will look at something where we find the radius of convergence of these. The book goes into a certain test that you can do to test for convergence, but we're not going to be covering that. Right. So we've gone through a couple of examples of these. We had gone through the sine and the cosine and the e to the x function. Let's see, let me grab my important series thing. Okay, this handout, which you'll have available to you for the test, we had gone through the expansion of the e to the x or e to the u function, sine, and then we talked about the cosine. So, and then here's the general format of the Taylor and the Maclaurin series, right? Okay, so let's see where we are then. Let's look at the natural log here. So there is both a Taylor and a Maclaurin series for the natural log. And this one then is actually a Maclaurin series. For the ln of 1 plus x. All right. And so this ln of 1 plus x, let's just write out some of the first few terms of it, it's going to be x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, etc. So you see it switches signs every term. And this is for the absolute value of x less than 1. And then just to write it as a general sum then, n equals 0 to infinity, okay, we've got that minus n. The first term is positive, so, actually, here, let's just start it at 1. We don't have to always start series at 0. And the first term is positive, so I'm going to represent it as n minus 1. To make it a positive 1 for the first term. And then that's going to be x to the n power divided by n. Right. And so you see these various terms satisfy that. And this also, this representation here is also on your sheet, right there, ln of 1 plus u. Okay. Right. Okay. All right. The next thing we're going to look at is actually a general binomial expansion or a binomial series. So this is called the binomial series. And it's called a binomial because inside the parentheses we have two terms. So what we have is in the parentheses, we have 1 plus x, close parentheses, and we're raising it to the k power. And k basically can be any real number. It doesn't have to be a whole integer. It can be a fraction. It can be a negative number. Any real number. All right. And we can expand this out. And basically, in college algebra, I think towards the very end of college algebra, you should have touched upon what's the binomial expansion, where you probably used Pascal's triangle and kind of expanded things using Pascal's triangle, if that rings a bell. Good. But this is the generalization of that. So what we have here is, okay, I'll just first write out the first few terms. 1 plus k times x. And so this is the k that is from the exponent. And then the next term is plus k times k minus 1 over 2 factorial times x squared. And then the next term is k times k minus 1 times k minus 2 over 3 factorial, and that's multiplied by x to the third power. All right, and then this continues on. And this is all fine as long as the absolute value of x is less than the number 1. The general way to write this is like this: the sum from n equals 0 to infinity of k choose n, that's actually how you say this, k choose n times x to the n power. And this is also called the binomial coefficient. Binomial coefficient, right? And then let me just write out what the binomial coefficient is, where this k choose n, so it's in parentheses, you've got the k on top, the n on the bottom, and its formula is k times k minus 1 times k minus 2, all the way to k minus n plus 1, and it's all over n factorial. All right. Now, I will tell you that for problems that you're going to be dealing with on the, say, the exam, we're just going to be talking about on this binomial series, I'm just going to be asking you to perhaps, say, list maybe the first 4 or 5 terms of it, all right? So you'll be using the formula in order to do that. Okay. And we'll go, let's see, where we have an example of this. We're going to be looking at an example of this later on today. Okay. All right. So that, I think, so, and we have, going back to this blue sheet then, we do have here's the binomial series represented, but except I just used the letter U instead of the letter X. And I think, and of course, this one at the very top, that's the one that we were using in the previous section. That's that geometric series. 1 over 1 minus u. And the only other one then here that we haven't explicitly touched upon is that tan inverse of u. This is the basically, this is the Maclaurin series for that. And I've written out the first few terms of it for you. So you'll have those available to you. Okay. Along with, I do want to point out, along with this other column has the radius of convergence of each of these. Okay. All right. Now, you know, these Taylor series and Maclaurin series, these go out to infinity, all right? Now, in practice, when engineers are working with this thing, they're not going to be summing things out to infinity. They're going to be summing things up enough to reach the degree of accuracy that is needed for whatever the project is, okay? So therefore, however many of the first few terms are needed get added up together, and that's the result. So what I have here then, so I want to say this, we can approximate a function f of x by a partial sum of the Taylor series. By a partial sum. Okay. And there's a notation for that I want to introduce to you. It's called capital T sub n. Let capital T sub n of x equal the sum of the first. Now, be careful here. This is the sum of the first n plus 1 terms of the Taylor series. All right. So it's sub n here, but it's the first n plus 1 terms. So therefore, let's say, example, say f of x, we're talking about the function e to the x power. Well, we have it, here we have it, this is the Maclaurin series representation of it, right? And why do I say it's the Maclaurin series representation? Why would I say that? No, right here. No, I'm asking here, what, on right up here, this, under the important series, Why would I say that's the Maclaurin series rather than Maclaurin series is a specific type of the Taylor series. But why would I say that? Because I just feel like it? Okay, because it's centered around 0, all right? Look at the Maclaurin series is just x to the n power here for it in its summation. The Taylor series is x minus some a. Maclaurin series is just a specific type of Taylor series. So if we have a representation like this, where we don't have u minus a to a power, we just have u to a power. So that means it's centered about 0. Okay? Do we see that? All right, so let's look at this. So this is our function here. And I'll even say here, and a equaling 0. So I'll even give you that in case there's some kind of doubt. And this, of course, means that we're talking about the Maclaurin series. Okay. Basically, write out the first 5 terms, or write out t sub 4 of x. All right. So t sub 4 of x, this is going to be the first 5 terms. And so we just go from our formula here. It's just a matter, in this case, it's very simple, just reading off from the paper here, 1 plus x. I don't have to write 1 factorial down here. 1 factorial just equals 1. So that's really not needed. Plus, okay, then plus x squared over 2 factorial, or just 2, because 2 factorial is 2. All right. Let's see, we want 5 terms, plus x to the 3rd over 3 factorial, which is 6, but I'll take either one, 3 factorial or 6. And then, let's see, that's 4 terms, x to the 4th over 4 factorial. That's 1, 2, 3, 4, 5. I better stop right there. Okay, that's 5 terms for T4. Notice that this right here, our representation, is really a polynomial. All right, we've got different powers of x, and we have different coefficients. That's a polynomial of degree 4, right? The biggest exponent in your polynomial, that's your degree of it. So this is a polynomial of degree 4. So T4 will be a polynomial of degree 4. T5 would be a polynomial of degree 5. T3 would be a polynomial of degree 3. All right? So let me just put this down here. So in general, T sub n of x is a polynomial of degree n. It's a polynomial of degree n, but it'll have n plus 1 terms. Okay? Any question just about that definition of T sub n? Okay. Before we just do an example with that type of thing, well, maybe I'll just do this example right here since we just talked about it. Example. Write a 3rd degree polynomial of the first 4 terms of the Taylor series for f of x equal to the natural log of x and it's going to be centered about 2. Centered about 2. So A here is going to equal 2, all right? So this is not a Maclaurin series. It's going to be centered about a non-zero number. Now, I did this kind of table here for your take-home quiz, and so I recommend this is the way to kind of organize your thoughts here, is just, first of all, let's just start out a little table. Here we have our n values, and they're going to be n equals 0, 1, 2, and 3. Okay, we're going to have 4 terms altogether. Okay, because this is going to be T3 of x. Okay. All right, and then in the middle column, let's put the derivative of the function, the nth derivative of the function. And then in the column next to that, then, we're going to evaluate or plug in our A number, which is the number 2. All right. And then once we've worked out this table, it's just a matter of plugging it into the Taylor series formula. Okay, so here, when n is equal to 0, we're talking about the original function here. So we're talking about not a derivative yet, but just the ln of x. Let's go down and do the derivatives first. Then when n is equal to 1, we're talking about the first derivative. So the derivative of the ln of x is going to be 1 over x. And then let's go on to the second derivative. When we get the derivative of 1 over x, it's going to be minus 1 over x squared. And then when we get the third derivative of minus 1 over x squared, we're going to end up getting 2 over x to the third power, right? So the powers will keep decreasing. Well, let's look at the derivative of, you saying this one right here, Jordan? Okay. Well, let's look at the derivative of minus 1 over x squared. That's the derivative of minus 1 times x to the minus 2 power, right? Because I need to bring the exponent out of the denominator. Now what happens then when I multiply the number in front by the exponent? Yeah, they cancels out. So I get a positive 2, and then I lower my exponent by 1, I get a negative 3. So it's 2 over x to the 3 power. All right, so that's our middle column. So then in the last column, we just plug in our A number. So this is going to be ln of 2. This is going to be 1 over 2. This will be minus 1 over 4. And this will be 2 over 8, which is, of course, I can reduce it to 1 over 4. All right. And then basically we just plug in. So we're going to want the first 4 terms. So the first one, well, it's just going to be, let me just write this out first of all. It's going to be f evaluated at 2 plus f prime of 2 over 1 factorial times x minus 2. So be careful here. We are centering it around 2, so it's not just x, it's in parentheses x minus 2. And then we're going to need another term, f double prime of 2 over 2 factorial times x minus 2 squared. So that's 1, 2, 3 terms. And then finally, f triple prime at 2 over 3 factorial times x minus 2 to the third power. All right. So now from our table, we were able to read off those various values of those derivatives. So f of 2 is just the ln of 2 plus f prime of 2 is 1/2. So that second term becomes 1/2 parentheses x minus 2. Now the third term we have f double prime is minus 1/4. So it's going to be minus 1/4 divided by 2. So that's going to be minus 1/8. Let me go down here with this. Minus 1/8 times x minus 2 squared. And then finally, let's see, f triple prime we found was reduced to 1/4. And what's 3 factorial going to be? 6. 3 times 2 times 1, 6. So 1/4 divided by 6 is 1/24. So plus 1/24 times x minus 2 raised to the 3rd power. Okay, so we've got our 4 terms, and this is a 3rd degree polynomial. Okay. And you don't have to be, in FYI, you don't have to be foiling this stuff out. Just leave it just like that. Okay? Question on that? All right. Here's a tricky one. So let's look at this one. This is another one where we're writing out the first few terms of something. Write out the first 4 terms of the expansion of the square root of 4 plus x. Okay. Now this is going to involve the binomial series, all right? So let's look at this. The square root of 4 plus x, for starters, that's 4 plus x raised to what power? The 1/2 power, okay? Now let's look at this binomial series formula here that's on the sheet. This one right here. Okay, notice what we have in the parentheses down here is 1 plus, well, I have you could have x, you could have anything. It's 1 plus something in parentheses raised to a power. So that's the first thing I want to point out to you. It's not 4 plus something or 3 plus something, it's 1 plus something. Okay, so what we have to do with this thing is we have to get this as 1 plus something raised to the 1/2 power, all right, in order to use our expansion formula. All right, so let's see how can we do that. I'm going to need to be multiplying something in front in order to be able to do that. Pull out a 4, okay, let's do that. Now, if I pull out a 4, is it going to be a plain 4 or is it going to be something else? It would be a 2. So, in fact, I can initially just write it like this. If I'm going to pull out a 4, which is what we want to do, it's really going to be the square root of 4 that gets pulled out. Because once it's no longer under the radical, it's not just going to be a 4, it's going to be the square root of 4. Now, in here then, what am I, and then this is also to the 1/2 power still. This then, because we pulled out the 4, this is a 1, right? The first term. Now, what's that second term going to be? X over 4, right? Because what we are in effect doing is we're dividing both of the terms inside the parentheses by 4, dividing both terms in the parentheses by 4, but that's with a 1/2 power on top of it, and multiplying in the front by the square root of 4 or the number 2. So we haven't changed the expression, we've just rearranged it a little bit. Is there any question on, so I'm going to rewrite this then as 2 times 1 plus x to the 4th, close parentheses, to the 1/2 power. Any question on that kind of manipulation like that to get it in the right format? Right. Now, looking at this sheet here with this binomial series, I deliberately wrote it this way with a general u there instead of an x. So in this case, what this x over 4 right here is going to be our u, all right, that I have in the formula. All right. So this, all right. So this is going to come out to be, now don't drop the 2 that we have there. This is going to be, we're going to have the 2 there. And so I keep the 2. Now I'm going to get, what do I need to get? The first 4 terms of the expansion here. So my first term, when we look at the formula, my first term is a 1. Here, let me do this. Okay. And you guys, all right, so the first term here is a 1. And then my second term is plus k times u. Now our k here, our exponent is 1/2, right? We're taking it to the 1/2 power. So this is 1/2 times u, but our u is x over 4. All right? Now let's go to the next term then. The next term then is going to be, well, we're going to be dividing by 3 factorial. Wait, Oh, wait a minute, I'm in the wrong one here. I have someone at the door for me. Yes, sir. Well, I don't know if it's working today, but Joe fixed the problem. It seemed to be a problem with my flash drive. But yeah, we've got it. Knock on wood, working. Okay. All right. So where were we here? Okay, we had done the second one here. So the next one then, we have a 2 factorial in the denominator. And then up above here, we have to multiply k times k minus 1. So we have 1/2 times 1/2 minus 1. And then it's u squared, so that's going to be x squared over 4 squared for my u squared, okay? So that's our, so how many terms did I say? Just 1 more, 4 terms, all right. Plus, and then the next one then is going to be 3 factorial on the bottom. And now we have k times k minus 1 times k minus 2. So that's going to be 1/2 times 1/2 minus 1 times 1/2 minus 2. And that's going to be u to the 3rd power. So that's going to be x to the 3rd power divided by 4 to the 3rd power. All right? Okay. Let me close my brackets right here. So the only other thing we need to do is clean this up. All right? But this is our basic format. Before we start cleaning it up, is there a question then of just the basic substitution into the formula of the k and the u, the x over 4 for the u. All right. So let's see here. Let's work with this. This is going to be 1 plus, this is going to be x over 8. And then what's 1/2 minus 1 is a negative 1/2, right? So that's going to be 1/2 times negative 1/2, which is negative 1/4. And that's going to be divided by 2. So that's going to be a negative 1/8. So let me put a minus 1/8. And I got the 4 squared here too. So that's going to be times 16, right? 4 squared is 16. And then that's going to be x squared. So I'll finish that afterwards. So here now we have 1/2 times minus 1/2 times minus 1/2, and then 1/2 minus 2 is what? Yeah, negative 3/2. So let's multiply those together. That's going to be 2 negatives get a positive. So that's going to be 3 over 2 is 8. So it'll be 3 over 8. And then I have 3 factorial. That's a 6. And then I have 4 to the 3rd power. That's 4, that's 64. All right. And that's all multiplying x to the third power. All right? So a little bit of arithmetic here. So let's finally get this thing finished. So we're now going to distribute the 2 and clean it up some more. So that's 2 times 1 is 2, plus 2 times x over 8 is x over 4, plus, okay, this is going to be what? 64, right? So that's going to be an 8. 8 times 8 is 64, times x squared. And then this one is going to, let's see, 2 into 64 is 32. So what's 32 times 48? Oh, actually, I can simplify first before I do that, can't I? I can take the 3 in the numerator, divide it into 6 in the denominator. So let's go on and do that. And then, let's see, then this 2 will cancel out that 2. So all I'm left with is 8 times 64 when I cancel the numbers. And that's 8 fours are 32. 512, I believe. So that's 1 over 512 times x to the third power. And, is that right? Yeah, okay. Yeah, I think that's right then. And so that's our answer then as a 4 terms. It's going to be a third degree polynomial. The tricky thing with a problem like this is the very first step that we did, is getting it in this form, 1 plus something to a power by taking out that 4 to the 1/2 power and then dividing both of the terms on the inside by 4. All right. Is there a question on this problem? Some type of problem you might see in the before Halloween. Okay. Huh? Might be it just before Halloween. Oh yeah. But I haven't finished it. So I'm kind of like halfway between. Halfway.
Be kind.
I'll try to be kind. I really will. Yes, Jen.
Well, I was like working on my own, and I got to the last term, I still started over 128.
Okay, so you got 128. Let's see what we got here. Okay, so we came up with positive 3 over 8. 3 over 8. We had a 3 factorial, which is a 6. And then we had 4 to the third power, which is 64. All right? But we got to multiply in front by 2. So what I did is I took divided by 3, and I got a 2 here. I multiplied the 2 here by the 2 there. So they canceled out. So all I'm left with was 8 times 64. I think it's right. Will's nodding yes, so that's an encouraging sign. All right. So did you? Okay. All right. All right. Let's see. Let's go back. So what we've looked at in the last couple of examples is just using the formulas, using a table to write out the first few terms of either a Taylor series or a Maclaurin series. All right. So couple other things I want to touch on in this section before we finish it up here, and that's this fact here. We can multiply and divide a Taylor series by simple polynomials. So we can multiply or divide a Taylor series by, and I just have this in quotes, simple polynomials, because that's what you would be encountering. So let me show you in a couple of examples of what I'm talking about here. So the first one is this. Find a Maclaurin series, for f of x equal x times the cosine of x. All right. Now, we already have at our availability here a nice formula for the cosine of x as a Maclaurin series. We don't have to reinvent the wheel here. In other words, we don't have to be getting the derivatives, and we'd have to use the product rule, right, if we got the derivatives of x times the cosine of x, right? And Acacia's going, yep, we'd have to do that. And so let's do it in a much easier way. All we do is multiply the Maclaurin series for cosine by x, and that's all we have to do. And it'll converge just like the other one does. So just multiply the series for cosine of x by the x that we have multiplied there. So we know that cosine of x is equal to this general summation, n equals 0 to infinity, minus 1 to the n power. It's the even powers, it's x to the 2n over 2n factorial. That's the formula for cosine. And so all we do is multiply by x. So x times the cosine of x is equal to the summation, n equals 0 to infinity, same minus 1 to the n, same dividing by 2n factorial, but what's going to be my new power of x here? 2n plus 1, right? We're just going to be adding. We add the exponent because we're multiplying by another x. So it's just x to the 2n plus 1. And this is our answer right here. Very, without much difficulty. Okay. Let's look at another example of something like this. Express e to the x minus 1 all divided by x as a series, or as an infinite series. All right. We go to our given formula here, and let's write out what e to the x is. And I'm just going to write out the first few terms of this. E to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the 3 over 3 factorial, on and on like that. So you see right there in the front of this summation is the number 1. So first of all, we just subtract 1 from both sides. And so we get e to the x minus 1 is then going to be the summation starting with the x over 1 factorial plus x squared over 2 factorial plus x to the 3 over 3 factorial, on and on like that. So that's, first of all, just what we've done. Now the next thing we have to do, we want e to the x minus 1 all divided by x. So then let's do that. Let's take what we've got here, divide everything now by an x. So what I'm going to get then here for my first term, that's just going to be 1, because that was x over 1 right there. So that's now going to be a 1. My second term then is going to be, instead of x squared, it's going to be x over 2 factorial, which is just 2. My third term, instead of x to the third, is going to be x squared over 3 factorial, and then that goes on and on like that. All right. Now, let's see if we can figure out a general formula for this. All right. So, basically, our first term, all the terms are positive. Our first term is 1, which is really 1 over 1 factorial. Then we have 2 factorial, 3 factorial. So basically, I can look at this like this, from n equals, well, we can go with 0. N equals 0 to infinity. All right. Then what would be my power of n here? This is really x to the 0 power, then it goes to x to the first power. So this would be x to the n power. But then notice here, when I have x to the first, I have 2 factorial. When I have x to the second, I have 3 factorial, and it would continue like that. So what would I have down here for x to the n? N plus 1 in parentheses factorial, right? Okay. And then that would be my representation as an infinite series. So it's a matter here of trying to find the pattern that you get from the first few terms. Now you could have written out another couple more terms if you needed that to help you see the pattern that's here. Yeah.
Okay, so sometimes we're just looking for the values, and sometimes we're just looking for like how to express those as series. Like, is that just what we're getting at?
Okay. Well, it depends on what the question is. All right. Here we're asked to express it as a series, all right? So that's what you're going to want to do. If we're talking about expressing it as a value, then that means plugging in a number. If we're talking about expressing it as, say, the first 4 terms, then we're only going to be writing out the first 4 terms. Let's see here. Yeah, that's pretty much the kind of stuff you're going to have for this section. All right? Okay. Now, let's actually ask another question here on this one. Okay, we figured out that this is the way we can write e to the x minus 1 all divided by x as a series. How about this question then? Express the integral of e to the x minus 1 over x dx as an infinite series. All right? Now, for starters, if we just looked at this problem without doing anything with series, I think it might be a little bit challenging to find the antiderivative of that. All right? That's just my take on it. I'm not even sure what U substitution you would use to get the antiderivative. So this shows in practice why this stuff that may seem not so important can actually be important. If we can get this I don't really know what the antiderivative is of this. If we can get this as a series, and then you say this is in practice, and approximate it to whatever error is acceptable, then we're fine without actually worrying about figuring out from a U substitution, which I don't even think you can do, what the antiderivative is. All right. So basically, we have this. We found out that e to the x minus 1 over x is equal to this summation, n equals 0 to infinity, x to the n over n plus 1 factorial. Now we're wanting to do the antiderivative of this. So we can then, it's just as simple as just doing the antiderivative, of course, of the other side, the antiderivative of our summation. But as long as this, for all the values for which this converges, I can just go on and do it term by term. So this is equal to the summation. Now I do the antiderivative on the inside of x to the n over n plus 1 factorial dx. The summation is n equals 0 to infinity. So now I just have to get the antiderivative of the individual term. And I'm finished with it. So we have that summation, n equals 0 to infinity. So we have an easy antiderivative to do. What's the antiderivative of x to the n over n plus 1 factorial?
to the n plus 1.
Yes, raise the power by 1.
Factorial.
Okay, times the factorial.
X to the n plus 1 over n plus 2.
Right, raise the power by 1, divide by the same, and then what's the other thing I'm going to put in the denominator then?
Factorial.
Yeah, keep the factorial as it is. It's a constant term, and then that's our answer. And I guess I should put in a plus c here also, plus general constant. So just remember that formula, that power series, that from sometime in the first month or so of Calc 1, that as long as n does not equal -1, this antiderivative is x to the n plus 1 over n plus 1 plus c, and that's what we're using here. Okay. Question on this one. Okay, we're going to look at another one kind of like this one. Yes, Jenna?
You take the derivative of factorial, does it always just stay the same?
Okay. In other words, if you have something like the derivative of, say, 1 over n factorial times x to the third, maybe, something like this, yeah. This is a number, okay? When you do it, when you have a number multiplying your function, the number stays, all right? But then I bring my 3 down and reduce my exponent. Okay, so that's a good question. Don't manipulate the number. It stays the same. All right, let's look at kind of a similar thing here where we're looking at an exponent function. And this is one that we can't find the antiderivative of. The antiderivative of e to the minus x squared dx. This is one of those functions that you can try as you like to do substitutions and all that kind of stuff. You're not going to get the antiderivative in the usual ways that we had learned. So what we're going to do here, and let's just say evaluate this as an infinite series. So that gives you a hint as far as what we're going to do here. We're going to use the formula that we're given, that e to the u is equal, and that's on that blue sheet of paper, is equal to n equals 0 to infinity of u to the n power over n factorial. And in this case, our u is going to be this negative x squared that's in the exponent spot. So therefore, e to the minus x squared is going to be the summation, n equals 0 to infinity. Now in parentheses, I'm going to put minus x squared, and I'm going to raise that to the n power over n factorial. So I'm just plugging in minus x squared for u. All right. Now, before we start to do any antiderivatives, I think it's a good idea just to kind of work with this a little bit, because otherwise we might end up making a mistake when we do the antiderivative. So let's look at another way, alternate ways of writing this very same thing. So we have negative x squared in parentheses raised to the nth power. Well, what's another way of writing just that? Okay, okay, you're saying negative x raised to the 2n power. No, that's not right. No. The reason that's not right is because you're then, the minus there is not being raised to the 2n power. Only the x is being raised to the power. The what on the bottom? With the x on the bottom? I don't think that's a good idea. All right. Yeah, and so what power would it have? Yep, n power. That whole parentheses was being raised to the n power. So that minus that's in there, I can take it out as a -1, but I want to raise it to just the n power, because that's my exponent there. But then the second part of what I have here is x squared raised to the nth power. Let me do it in 2 steps. And this is all over n factorial. All right, so, and then how can I rewrite x squared taken to the nth power? X to n, right. So I can just take this thing, now it's n equals 0 to infinity, -1 to the n. Now it's x to the 2n power all over n factorial. The reason you want to separate things out like this is that once you then go and try to find the antiderivative, this is much easier to work with, because all you do is have a bunch of stuff times x raised to some kind of power. And it's much easier that way to get an antiderivative or a derivative for that matter. So you want to fiddle with it a little bit, and you'll get this. So now we're ready then to get the antiderivative of e to the minus x squared dx, and that's just going to be the sum of the individual antiderivatives here. So I'm going to put the summation, I'll put my integral sign, -1 to the n, x to the 2n, all over n factorial dx. So I've got that little integral in there, and let's get its antiderivative. So again, it's the summation from 0 to infinity. Now, what are we going to get then for this antiderivative right here? Am I going to fiddle or do anything with that -1 to the n? No, just going to keep it as it is. So -1 to the n. Same goes with that factorial down in the bottom. I'm not going to be messing with that. But I've got x to the 2n, so what's that going to become? Right. Increase the exponent by 1. And whatever I've got up here, I then have to put down here. When I teach the basic calculus class, I say it's like matching bookends. That new exponent that you get has got to be matched in the denominator. And then plus the general constant c. And that's good enough right there. And so what we've been able to do then, for this function that we could not get an antiderivative of, we've got it here as this infinite series. And so whatever approximation, whatever level of error is acceptable to us, we can just use that to evaluate it. Does that make sense about level of error? Well, okay.
What would you use that for?
For engineering, that's the thing that comes to mind for me. You've got a certain acceptable tolerance level of what you think can be, and so you've got all these terms. This becomes x to exceedingly bigger powers. So this x, this has to be for where it converges. By the way, this is for the absolute value of x less than 1 that this is going to happen. So we're talking about fractional values, and then they're going to get smaller and smaller and smaller. Okay. The book talks about some error analysis and that kind of thing. I've really not talked about that. Trying to keep it to what we do need to know, but if you're curious, Jenna, there's material there in the textbook about it. All right. Why don't we take a break? Gosh, it's almost 10 after. Why don't we take a 5-minute break? I think I'm almost finished.
No, I will make one of those. I'm ready to make one here. Okay, so I turn off the thing.
Yes, sir. When we're doing antiderivative, it's the same thing if you look at just from Calc 1. If you're doing the antiderivative of, say, 5x squared dx, all right, you don't mess with this 5, you just keep it. And then it goes x to the 3 over 3. All right, it's the same thing here. Those are just symbolic representations of numbers. All right, so this minus 1 to the n, it's going to, so depending on what value n is, this is just a constant number. If n is even, it'll be a plus 1. If n is odd, this will end up being a negative 1. And for this factorial, again, for every specific value of n, this is just going to be a number of some kind. So just like with the 5 here, when you do an antiderivative with just your number part of it, it's all a constant. You just don't mess with it. You keep it as it is. Yeah, this stuff. So remember, in front of this thing, we have this summation from n, say, n equals 0 to infinity. So sometimes this will be a positive, sometimes it'll be a negative, and then this will vary. It's not a variable. It just, as you expand it, it becomes 1, and then 2, and then 3, and 4 factorial. But nonetheless, it's still a constant number. So when you do the antiderivative, you don't mess with it, but you just deal with the x. Yeah, exactly. Okay. Have you been in touch with Anne?
Amy?
Amy.
Yeah.
Mhm.
Yeah, yesterday. Because she wanted me to email you.
Mm-hmm.
She texted me after.
Mm-hmm. Okay.
I just working with medication when you want to increase something to get like an infection, and then if you wanted to increase it in small doses, this could be like
Who knows?
Well,
I mean,
I'm kind of looking at
I'm gonna say, who knows?
Stop eating sandwiches, it makes me hungry. Not to be.
You're always hungry. You're
Yeah,
going to class. You're
I
very
should, but I don't think about that stuff.
When I was your age, I was probably even skinnier than you are, or thinner. Sorry, than you are. I don't like the word skinny. That's a derogatory word. You can eat anything under the sun. Never gained any weight. What happens, Kyle, is when you reach 40. Seriously, I don't know. Something happens because it's not just me.
I keep thinking, like, I'm driving, like, man, it's probably not even 40.
It's depressing, but you know what? Yeah, it's all right. It's not a weight problem. It's all right.
Yeah, but now I keep thinking, like, I should probably not even McDonald's to be like, I'll go straight to like, probably.
You could probably use some McDonald's.
Yeah.
Yeah, McDonald's. No.
I need weight.
You never know what's in the hamburger.
Yeah, what? Did you see that article, like, about their chicken?
I don't
Like,
need
the
the chicken.
whole chicken, like, even the eyeballs and bones and everything, like, grounded up. Like, it's not even real.
Oh, wow.
And then they coated it in ammonia. Or something like that.
What, they was coated in, what, a household cleaner?
They coated it in bleach and then they washed it off. Like, that's poisonous.
Was that about chicken?
Well, I admit that sometimes in a pinch I confess a weakness occasionally to their Big Mac with a secret sauce.
I want you to net that way. I can't do it. It's pretty close to 1,000 Islanders.
It is actually. It's not. It doesn't seem so secret, really.
Except for they just put a lot of extra stuff.
Yeah, that's good. Yeah, that's the charm. That's the charm of McDonald's. All that extra stuff that they put in things.
That's what I look at, an extra step.
Mm-hmm.
You asked something about that, right there.
Okay. Really, I have just I just have one more example here in this section, and then we can just start to look at some review stuff, I think, And by the way, for Monday, what I do recommend for Monday is if you have questions, think of things that you're concerned about, or specific problems that you're concerned about, and I certainly would like to entertain questions from you first, rather than me just go on with just doing what I want to do, okay? So it's a review time, and so think about what you might want to bring forward at that time.
Wait, we did next on Monday, we just bring random questions, like from the homework quiz?
I can look at some things from, yeah, I'm willing to look at some things from this, certainly. Yeah, I'm willing to do that.
Good.
We're not going to do the whole take-home quiz on Monday, but I'm willing to look at some things there that you have. Okay, so this is another problem here. Express cosine of x squared over 3 as a Maclaurin series. And hopefully you guys have the general idea of what we need to do here. We just work off of the formula for the cosine that we have listed here. A cosine of u is the summation n equals 0 to infinity of minus 1 to the n power, and it's the even powers, u to the 2n divided by 2n in parentheses factorial, all right? And then what we just do is and let's also put here and give its radius of convergence. And yeah. And give its radius of convergence. That would be a good one too. All right. So we just plug in x squared over 3. Yes?
What's the difference of the radius of convergence and the interval?
Okay. The radius of convergence is basically the length, half of the length of the interval in which it's convergent on. So say something, if it's convergent for the absolute value of x minus 3, then this is the radius of convergence, it's 3. Now, if it's something like 2x less than the absolute value of 3, then dividing by 2, the radius of convergence is 3/2. But so this is radius of convergence. It's basically half of the length of the interval. This is absolute value of x less than 3 is all the values between minus 3 and plus 3. This thing has a length of 6, and radius is 1/2 of that. So the radius is 3. This thing also ends up having a radius of convergence, a radius of 3/2. Because this is going to be x between 1.5, 1.5, and minus 1.5. That's a whole length of 3, but we've cut it in half. The radius is 3 over 2. Okay? Now, the interval of convergence is when you have to test the endpoints. And I'll tell you if you have to test the endpoints. So if you have to test the endpoints, if you have to test the endpoints, say for this one, so for this one we're talking about absolute value of x less than 3 greater than minus 3, all right? So we would have to test 3 and negative 3 in our series to see if it converges at either one of those. Let's suppose it converges at 3, but diverges at negative 3, just for instance, as an example. So therefore, our interval of convergence interval of convergence, we would not include the -3 because it doesn't converge there. Interval notation, comma 3, but then we put a bracket there by the other 3. Okay. Does that help?
So on the side of your event, how often we need to have that?
Right. Yes.
So it's not $1.
Okay, that sounds reasonable. And I'm not trying to steer you wrong. No, that's... All right, well, let me just start over. Well, here. Let's put this up here. And so basically, what do we have to do here? We have to plug in what for what? X squared over 3 for what? For the u, right. So plug in x squared over 3 for the u. So we have, therefore, the cosine of x squared over 3 is going to be that summation from n equals 0 to infinity minus 1 to the n. Now, in parentheses here for the u, for right now, I'm going to put x squared over 3, and now that's being raised to the 2n power, and then it's all over the factorial of 2n. All right. Now, if I tell you to simplify a little bit on the inside, then that's what you would need to do. If I don't say simplify, then you could just leave it like this. But if I do, you need to do a little bit more work here. So this would be minus 1 to the n. Now that parentheses there, that's all being raised to the 2n power. So what power is my x alone being raised to? 4n, 2 times 2n. So it'll go to the 4n power. And then that 3 is in the denominator, so that 3 is going to be raised to just the 2n power, right? 3 to the 2n. And then I still have the 2n factorial in the denominator. Okay. And this is fine. Now this 3 to the 2n, I could also change that a little bit if I so chose. How could I express 3 to the 2n using a different base? What's 3 squared equal? 9 to the n, right. That could also be written as 9 to the n power, right? Okay. 3 squared, then raised to the n power, 9 to the n power. Okay, so this is my representation of cosine of x squared over 3. Now, let's see, radius of convergence. Actually, that's not such a interesting question after all. This cosine one, if we look here on our paper, this cosine, the radius of convergence is all numbers from minus infinity to infinity. So the same thing would happen here. The radius of convergence for this would also be from minus infinity, will be infinity. So either writing it like this or saying r is equal to infinity, either way, it's the same kind of thing.
How do you know that's infinity?
Okay. That second column there on that page shows the different radiuses of convergence. Okay, so I think that's good enough here for the Taylor and Maclaurin series. Now, we have a little bit of time left. I thought I'd actually look at the well, let's look at this. Is there something on the homework or the take-home quiz that's really confounding anyone here? And I can just at least get it started maybe without doing the whole thing. And I know all you folks out there are having absolutely no problem with the homework and the take-home quiz. You've probably done it already and are just biding your time to turn it in. Not, but okay, who knows? The quiet majority out there.
On the homework assignment we just turned in, number 11.8.
Let's see. Here. Did I bring that stuff?
I can do it.
No, I didn't bring them. Which one? Show.
The very last problem. Where's your paper? On the back.
Oh, okay. This is in the, what section was that, 11.8? Number 26, 11.8. All right. Okay, so what is it? The summation n equals 2 to infinity x to the 2n over n ln of n squared. Okay. All right, n ln of n squared. Okay. And did I leave a hint there to do the ratio test?
That's where I tried it.
Okay.
And then when you did it, I did the ratio test, and then I ran the limit. The denominator was 0, or something like that.
Oh. All right. Let's do that. So, because I've done, well, let's try the ratio test. Let's see what happens. I don't really like the looks of that, though, for the ratio test, but the only other thing would be the root test on this, so I wonder about the root test. So let's look at the nth root of the absolute value of x to the 2n over n times ln of n squared. See what happens there. So the first thing, the top thing then, and we want this to be less than 1, right? So the top part would be what power of x then, if I'm taking the nth root of x to the 2n? X squared, right? And then this would be and the bottom here, this would be the nth root of n, and then we'd have the nth root of, let's see, that's the thing that's bothering me, the nth root of ln squared. Okay, we know that the nth root of n is going to go to what as n goes to infinity?
1.
Goes to 1. That's on that strategy sheet there. That goes to 1. And let's see. ln of n, that's going to be to the 2 over n power. We're squaring it and then taking the nth power. I wonder if we would So this would be an infinity to the 0 power, right? For if we want to see, try L'Hopital's rule on this. Let's take the ln of this. So this gives us 2 over n times the ln, oh gosh, of the ln. Okay. And then, let's see, this is going to go to infinity, that's going to go to infinity. So, let's see, so we have 2 over x times the ln of x. That's what we're dealing with. And if we do the derivative of the top and bottom, the derivative of the bottom is just the number 1. Derivative of the top, we have 2. Okay, this is actually going to be 1 over the ln of x times the derivative of the ln of x, which is 1 over x. Okay. So what we have here then is 2 over x, ln of x, as x goes to infinity. I think that's right. Which is 0.
Down to 2 over n. Well, ln of n is 2 over n.
How do you go from that x squared roll back to natural log into
Oh, from here, I don't know, how am I going from here to here?
how do you go from there to there?
From here to here?
Yeah.
Well, what I'm looking at, I'm trying to figure out what this is going to go to. The nth root of n goes to 1. Okay, that's just a fact that you can memorize or know. The nth root of n goes to 1. So I'm rewriting this as, this is the ln of n squared, and I'm taking the nth root of it. So this is the ln of n to the 2n power, all right? Oh, I see what you're saying.
Because then we would have had 2 times ln of n over n, and then
Oh.
bigger the whole thing was just gone to 0.
Wait a minute, let's see. Right. Yeah, why did I suddenly put the L? Let's see. We're trying to figure, because to do the 0, all right, we got ln of n to the 2n power. Do you see that, Jordan? Yeah. Okay. And then this goes to infinity and this goes to 0. So it's what we call the infinity to 0 case. So you take the natural log of it to see what the natural log goes to. I want to try to use L'Hopital's rule. And it basically, so I take the ln of this, so I take the ln of n to the 2n power.
So you bring the power down.
Yeah, so I can bring the power down, exactly. So that gives me 2 over n times the ln of n. And then this gives me a numerator and denominator. The numerator goes to infinity, the denominator goes to infinity. So I can use L'Hopital's rule. And what I get then is, and this is the function that I'm really using, 2 times the ln of x, ln of the ln of x over x. And if I use L'Hopital's rule with that, the x becomes a 1. The derivative of the ln is 1 over the ln times 1 over x, just using the chain rule, right? And so this becomes 2 over x times the ln of x. Well, both x goes to infinity, ln of x goes to infinity. So as you said, this whole thing goes to 0. Well, if the ln goes to 0, this is from test number 1. If the ln goes to 0, then what's the function going to? What's e to the 0 power?
1.
It's going to 1, right. So therefore, this is going to the number 1. All right. What's the question asking? For the radius of convergence of this thing? Is that what it's asking? Right. So it looks to me like, and let me check the answer. It looks to me like the rate. Both the denominators are going to 1. So it's just, we're just looking at, when we look at the limit, then the absolute value of x squared has to be less than 1. Okay. Oh, I know another way, an easier way to do this, I think. Well, if the ln of n is less than n, we know that, that's another fact. Therefore, this 1 over n times ln squared, this is going to be greater than, no, I don't think that's going to work, greater than n to the third. I don't know if that's going to work or not. Cancel that out. So I'm saying that we have to have the absolute value of x squared be less than 1, which means x has to be less than 1. Yes? So that's that. I don't think you're going to see that on Wednesday.
When I was doing this last night on my homework, I used a website that helps you step by step to do things, and the way it told me to do it was do the ratio test. And then once you get to this step right here, where you get x squared, you do the ratio test, and it still leaves you like a lot of stuff in there. And what it did was it took that x squared on the absolute value of x squared and put it on the outside, and then you took the limit. And then you, all you had was n over n plus 1, and then you had ln n squared, and you get over there.
Right, and so you have a bunch of stuff that just goes to 1. Yeah. Yeah, the ratio test would have been a little bit easier than the root test. Either way, though, it's going to come up with that then. Did it want you then to also test the endpoints to find the interval of convergence?
Yeah, you find
Right. Actually, that wouldn't be something bad to look at here. Let's just take this n times the ln of n squared as n goes from 2 to infinity. Okay, so by hook or by crook, we found that the absolute value of x has to be less than 1. So that means x lays between -1 and +1. So what happens at the two endpoints? Let's look at 1. So we plug in 1 in here for x, and we basically get 1 to a power is still 1. So we get 1 over n times the ln of n squared. And let's see what happens with that. One thing that comes to mind that I could use with this is the integral test. That's one test that I could use. This, I can figure out the antiderivative of 1 over x times the ln of x squared using u equal to the ln of x, using a substitution. So I can figure out that, and this is also a positive decreasing function. So those are the two things we have to have for the integral test. The function, as n gets bigger, the value gets smaller, and it's positive in value. And let's just see what this would be. ln keeps getting bigger and bigger. The denominator keeps getting bigger for the ln, and the n keeps getting bigger. When your denominator keeps getting bigger, your value keeps getting smaller. All right, so that's how you just know. You could also do the derivative, but why go through that if you can just say that, hey, the denominator is getting bigger, so it's getting smaller. Does that make sense to you? Okay. So here, this is really 1 over x times the ln of x to the -2 power. And if I have u equal to the ln of x, du is 1 over x dx for my substitution. So this just becomes u to the -2 power du when I do that. And so when I take the antiderivative, this is u to the -1 over -1, which is -1 over the ln of x. And what happens then as we go from 2 to infinity here, does this converge or not? Don't be so quick. just the ln of x approach as x keeps getting bigger and bigger, just the denominator. No, it doesn't approach pi over 2. The ln of x keeps getting bigger and bigger and bigger. It gets bigger very slowly, but it keeps getting bigger and bigger. The ln of x, as x goes to infinity, is equal to infinity. So this bottom here, as x goes, for the first filling in, this is going to be basically 1 over infinity, so it's going to be 0. So this is 0, double negative, plus 1 over the ln of 2. So it converges so this would converge by the integral test. Right? And then also, if we did x equals minus, and same thing then, well, for minus 1, what happens with minus 1? If I plug in minus 1 there, what's minus 1 raised to the 2n power always going to equal? No. Is 2n is 2n an even number or an odd number? So negative 1 to an even power is always equal to 1. So it's the same thing. It's 1 over n ln of n squared. It's the same deal. So it converges at both of the endpoints, all right? Minus 1 to 1. Thanks, Will. That was a good one. Let's hope the random number generator doesn't hit on number 26 as the very last one. All right. Anything else that, and again, this is either from the homework or the take-home quiz.
I actually just crossed it off.
You just decided we weren't going to look at that one. Yeah. All right.
It was hard.
Yeah, it is hard. It is hard. I'll grant you that. Yeah. So we're okay, huh? I guess I have my sense is probably that's not due to Wednesday. The take-home quiz probably hasn't been looked at too much. That's I wasn't born yesterday, so I know that that's probably the case.
There are other classes.
What's that now, Sandy? Well, we know Jen is a special case.
It's more problems than
All right. Well, let's just look at we've got a couple minutes. I know you think I'm just such a drudge. I'm going to keep you here to the last minute, but oh well. This is just from the practice problems here. If we've got a sequence like this, 5n squared plus 4, over 2 minus 3n cubed. So this is a sequence. It's not a series. What's the limit as n goes to infinity of this thing here, of that expression? How would we go about trying to figure it out? This is from the practice set, those blue pages. Yes, exactly. So you've redeemed yourself. We do divide all the terms by the biggest exponent here that we find, and the biggest exponent is n to the third. So we take 5n squared over n to the third plus 4 over n to the third over 2 to the n to the third minus 3n to the third over n to the third. Okay, so this is a systematic way to figure this out. So basically then this just becomes the limit as n goes to infinity of what? This is what, 5 over n plus 4 over n to the third. Those are both going to go to 0 as n keeps getting bigger. The bottom, we have 2 over n to the third. That's going to go to 0. And the other one is minus 3 times 1. So that goes to minus 3. So basically, it's 0 over negative 3, which is 0. And that would be our limit then of this. Okay? What about this one? this is, again, it's a sequence, 4 times negative 2/3 in parentheses raised to the n power. What would be the limit of this particular sequence as n keeps getting bigger and bigger and bigger? Now, we're not adding anything up. This isn't a series. It's just a plain old sequence. So that negative 2/3 keeps getting raised to bigger and bigger and bigger and bigger power. Where do you think we're headed with this value? So we have 4 times minus 2/3 times minus 2/3 times minus 2/3 times minus 2/3. Yeah, 0. Right, all of these, once we keep multiplying by this fraction, we get close, we get smaller and smaller and smaller values that start to, they go positive, negative, but they keep getting smaller and smaller around 0. So that's exactly where we head here. It equals 0. We're not summing things up. This isn't a geometric series. It's just, we're just looking at where it equals 0. But what about this one? And we'll stop with this one. Let's look at the a sub n equals 6 times 5/4 to the n minus 1 power. And we want to look at the limit of this as n goes to infinity. Now we have 5/4. Is 5/4 smaller than 1 or bigger than 1? Bigger. Bigger than 1. So we keep multiplying it by something that's bigger than 1. So where do you think this thing is headed? Infinity, right. It's just going to keep getting bigger and bigger and bigger. So the limit there is just going to be infinity. Okay. All right. So see if you can come prepared with some things on Monday rather than me just springing it on you. And certainly willing to entertain things. And I'll bring my solutions with me so that if I do get stuck, I can unstuck myself. So anyway, have a good weekend, and let's hope we win, win, win. Yes.
Okay. So, you know how you gave us that sheet that says, like, if we have this, then we should do this? Is there, like...
Oh, you mean the strategy sheet? Mm-hmm.
Well, I was trying to, like, read back through my notebook, but I was getting really confused at my notes somehow.
Mm-hmm.
Like, is there a way maybe you could, like, make a sheet, like, if we're going to use the limit test, like, you know, what, we need to have these conditions and, like, this, like, we need to, like, it needs to be this, like, for each test, or would that take forever for you?
It's really on that sheet. You don't have it with you, do you?
Yeah, I do.
Yes, George.
I'm not sure, summer camp, drinking late.
And turn it on Monday then, okay? Okay. Right.
Like, and for some of them, if the limit equals 0, then it converts to the current limit. If it doesn't, like, I'm getting confused. Because it tells us, like, when we need to use the test, but it doesn't tell us what we need to do for that test. Like, I'm getting confused from my notes.
Well, one thing we have here, if it's similar to a p-series or a geometric series, then we're going to use either one of these two tests. Now, I can't specifically tell you which one we're going to use, but we're going to use one or the other. So that's one thing right there. And this is what I told you about what similar to a p-series means.
Right. I mean, I get that, but I'm saying, like, when you use the limit comparison test, like, I don't know what I'm trying to say.
Well, you use the limit comparison test when you can't use the comparison test. All right. So something like, if we're looking, just a very basic thing, if we're looking at n squared minus 1, for instance, 1 over n squared minus 1. No, let me do plus 1. Greater than, the minus bigger, smaller than the greater. Yeah, let's do this one. And then equals, I guess n to the starting 2 to infinity. Now, if we try to directly compare it with 1 over n squared, which is the obvious choice, right? Okay, the p-series. Notice that n squared minus 1 is less than n squared. So when we do the reciprocal, it's greater than 1 over n squared. So we know that this converges. If t is equal to 2, it converges. But this is what we call the comparison test, where we're directly comparing bigger than or less than. In this case, we can't use that test.
Right.
Okay, that's what I mean when you can't use the comparison test. Then we want to go to the LCT, the limit comparison test, all right? And then what we compare then is we look at this, 1 over n squared, over this, and we look at the limit as n goes to infinity. And as long as it equals a finite number, and we talked about this the other day, it doesn't have to equal 1, but as long as it equals a finite number, and I think in this case it will equal 1, then we know that if this one converges, which it does, then this one converges.
Okay.
That's the purpose of the LCT.
So what's the thing if it equals 0, it converges?
Okay, you're talking about the ratio. I think you're talking about the ratio or the root test. Oh, no, I know what you're talking about. You're talking about this fact. Do I have it on here, or is it in? It might be.
The test for divergence?
Is this how I put this? Because that's where I plugged in that. Did I run out of power? That aggravates me if that's what I put there. So this should be, if you can see at a glance that the limit does not equal 0, then the test for divergence should be used. What you're talking about, Jenna, is this. If we have a series of AN.
Can we use the test for divergence on that problem?
What, on which problem?
That problem.
No, because here, because this is the convergence test. If the limit of AN as n goes to infinity doesn't equal 0 or does not exist, then it diverges. So it really bothers me that that's what I put, that I didn't correct that correctly. Because this is something we know, that if this converges, then the limit of the AN goes to 0. This is what we know. This is a fact. It has to keep getting smaller and smaller and smaller for that sum to converge to a finite number. Okay? So we just turn it around. So if the limit does not equal 0, then it diverges. And that's called the divergence test.
Okay, so why can't I just see, the problem would just say, why can't I see if the limit as n goes to infinity of 1 over n squared minus 1, if that doesn't equal 0, then it converges. And if it does equal 0, then it converges. Why can't I do that for that?
But what's the limit? Okay, so what was the one we were talking about? 1 over n squared minus 1. What's the limit as n goes to infinity of this?
It's going to be 0.
So then it converges, why can't I just say that?
No. No, you can't. Because look at this summation, the harmonic series. We know that this is a divergent P-series, diverges. What's the limit of this as n goes to infinity?
Zero.
Hmm?
So it's only conclusive if it doesn't equal zero.
Right, that's the divergence test. If that term, the limit doesn't equal zero, then it diverges. But if you cannot say that if the limit of this term equals zero, then it converges. You can't say that.
You can only say if it converges, then
Then the limit's equal to zero. That's a different statement. Okay? And I've got to correct that.
Okay, so if the limit, if it goes to infinity of a to n does not equal zero, then, no, but it says, then the test should be used.
Right. Right. That's the divergence test, right?
How do you get does not exist? Like if it's one over zero?
No, if you have something like, minus one to the, let's just say you have this series. Okay, and this is our a sub n right here. And we look at the limit as n keeps getting bigger and bigger and bigger. Well, when n is even, it becomes a positive n. When n is odd, it becomes a negative n. So it's going to go to both, part of it's going to go to negative infinity, and then part of it's going to be going to positive infinity. So in that case, the limit doesn't exist because the limit's only one single number. Do you see how that branches off two ways? Yeah.
Okay, but like, that problem is pretty easy. Like, say if we have a fraction, like 1 over n squared, for instance, like, how would we know that it does not exist?
Well, let's look at something like this.
You can divide by the n squared, and then you get 5 over 0, which is equals to 0.
No. Let's see. Yeah. Okay. So what you're talking about is dividing by n squared. Okay, let's try it. So it'll be 5 plus 2 over n squared over 4 over n. All right. And this is as the limit as n keeps getting bigger and bigger and bigger.
Because that's just going to equal 0.
So as n keeps getting bigger and bigger and bigger, this keeps getting smaller and smaller and smaller, right? And what happens when we divide by smaller and smaller and smaller numbers? We get bigger and bigger and bigger numbers.
Oh, it's going to infinity. It's not,
Yeah,
so that doesn't equal 0.
infinity.
That doesn't equal 0, that's infinity.
The whole thing is infinity. This limit here is infinity. Another way of dividing this thing could have been this. Just divide it by n, and we get 5n plus 2 over n over 4. And then when we take n going to infinity, this goes to 0. That just stays at 4, and this goes to infinity. So the limit also, that's another way of seeing it, that it also goes to infinity. So this thing, if you can, this kind of thing I'm talking about, eyeballing it, then you can say that this diverges by the divergence test. Because this term keeps getting bigger and bigger and bigger, it doesn't go to 0.
I think I was getting confused because every time if I did that and then it equals 0, then I said it diverged.
Well, and that could be because of what I put on that piece of paper there. Right. Which bothers me a lot.
I think it might have been in our notes too. Because I think that homework was before you gave that out, but I don't know.
No. I might screw up, and I know that I didn't say in class that if the limit is equal to 0, then it diverges. I know I didn't say that.
Yeah.
Yeah.
All right, well, thank you.
All right.
Have a good weekend.
You too. Hmm.